Hi everyone, and welcome to the guided notes section for inverse functions. Just do a quick little erase here, and we'll start talking about how to find an inverse function and what that means. So first, given this set of ordered pairs, I ask you to find the inverse points. The inverse is found by switching the x and y values. What that means on a graph is that you'll be seeing a reflection over the line y equals x. So the new points would be -2, 3, or the points of the inverse rather would be -2, 3, 5, -1, and 0, 4. It's hard to see the reflection over the line y equals x with a set of ordered pairs, but we can plot the points nonetheless and take a look. -1, 5, and 4, 0, and then -2, 3, over 5 up 1, and over 0 up 4. Again, not much really to see visually, not very obvious, but in concept, we're taking a reflection over the line y equals x when we find the inverse, and we are switching the x and y values. Okay, in the next example, what I'd like you to take a look at is the table of values, where you can see, once I've made the inverse, that I've simply switched the x and the y values between these two functions. Give me a moment. So they just flip-flop. They just switch places, and that's that. It's as simple as that. So the question is this an example of an inverse function? And the answer is no, because these two x values repeat once I switch the x and y values from the original and make the new relation. The first function will pass a vertical line test because it has no repeating x values. If you were to plot those points, you'd see that it would in fact pass a vertical line test, but it wouldn't pass a horizontal line test because its y values repeat. Since I'm switching x and y to find the inverse, that's why the inverse won't be a function, because the x values will repeat. Right? So, is this an example of an inverse? No, because the second function, the inverse function, inverse relation won't pass a vertical line test. What that means is that in the beginning, again, the original may have passed the vertical line test to show that it was a function, but it didn't pass the horizontal line test. So what we see is that both functions will have to, in this case, won't pass a vertical line test, therefore the inverse won't be a function. Okay, now I'm going to move on to looking at these graphically. When I graph the inverse of this function, and it may help, I suggest to list the ordered pairs, you go through the point 0, 0, 2, 2, and -2, -2. And though that may not be of much help to you now, what this ends up looking like, if we take that concept of a reflection of over the line y equals x, is that I've got a function that looks like a mirror image of the original reflected over the line y equals x. You can see the symmetry even if you aren't able to identify it. The black line has flipped over that little dotted red line to become the blue function now. Now, are both of these functions? Yes, the black one is a function. It passes the vertical line test. Is this an example of an inverse function? Yes, it is, because both the original and the inverse pass the vertical line test, and the original passes both vertical line test and a horizontal line test. If the original passes a horizontal line test, it means that its inverse is in fact a function. Okay, that's the end of this first video. Stay tuned for part 2.